going to look at a little bit more detail in wafer processing. Dr. Kai will go into more details. Okay. So, right. So if we are ready or more or less ready, yes.
Can I ask a question? I was thinking like there are a lot of talks like about other semiconductor like elements that are made from semiconductors are made from like not silicon but graphene and other things.
Yes.
Using the tool with the sports or silicon?
Yes, there is. We will look at a property that is technically called band gap that these semiconductor materials have. So any material that has got a band gap is basically a semiconductor. And graphene has got a zero band gap, but still it has got some band gap, so it's called a semiconductor. So it comes from there. But we'll look at it because we are going to describe the technology and science a little bit, so you will get answers to that. Okay. So now we are looking a little bit at silicon wafer processing. What we had before is earlier was an overview of the fab process and the industry and so on, so that you get to know a little bit about what the lay of the land is, where everything happens. So now we look at it in a little bit deeper detail. So here's a little bit of fabrication overview. So when we fabricate wafers, what we are doing is that we are starting from a blank wafer that's got nothing on it. It's just a piece of silicon, the round disk of pure silicon that we have got. And when we get finished with that, it will take from 2 to 3 months for each wafer to get from start to finish. And in that time, it is continuously going through the fab through various processes. Now, fabs run 24 hours a day. There's not like a 9 to 5 working arrangement. They work 24 hours a day, and they work 365 days a week. They never ever shut down unless there's a big earthquake or something, or war starts, something like that. They are not shut down. And the reason why it happens like that is because the tools are so expensive that if you work with them only for a few hours, you cannot recover the cost of buying them. There's no way to do that. So the only way to justify the cost of buying the very expensive equipment is to run them for years and years and years continuously. So that means that tools do break down and so on. So, but in the industry, if say our washing machine or something breaks down, then we can call a plumber or get somebody, a handy person, to come and fix it. But not so. But that's not the way that semiconductor industry operates. It's got lots of tools and very expensive tools and equipment. And things keep breaking, and that is why we need all this trained workforce, this trained manpower to fix it very, very quickly. Otherwise, it's a commercial operation. There will be big losses. And normally, what happens is that a person from the tool maker is permanently stationed there. So if you bought a tool from a company like, say, KLA Tencor or Lam Research or Applied Materials, then a person or persons actually sit in the fab. They're 24 hours. They are on call to come and fix the tools from their company. So it isn't like phoning anybody and that's it there with all spare parts with them. Sometimes it does happen that some spare part is not available, and oh well, this thing, it needs to be flown from Singapore. Then it needs to be charted very, very quickly. It needs to be brought in. So this is a very high pressure work environment. That's important for people to work in there. The pay is very good, but at the expense of a lot of work pressure that you have to work over long hours and work under very strict guidelines and high degree of precision and so on. So the work normally goes like this, that you work that there's a team that starts work, let's say from 7:30 in the morning, and they'll work until maybe 6 o'clock or 5 o'clock in the afternoon. Then at that point, the evening crew will come in, and that will take over from them, and that will take everything sustaining the wafer production throughout the evening and night hours until the next morning, and then by 7:30, that'll hand over to the normal morning crew. In between that, usually have meetings. When this handover takes place, there's a meeting, so that one crew can inform the other crew what's going on, where are the various wafer lots, which equipments are having problems and what those problems are. So all of those need to be figured out. So there will be all these things. So the process are carried out in various specific process tools that can do various different processes that we'll look into what those processes are. Each process module or tool is overseen by specific engineers and technicians that work on just on that particular process. So this industry is highly specialized. If somebody is working on etch, they'll not usually ever send them to do, say, metal deposition or lithography. They are specialized people. So if you work there or people work there as engineers, then there are etch engineers, there are litho engineers, there are deposition engineers, there are diffusion engineers, there are implantation engineers that work in their own fields and with their own tools that do not migrate from one sort of thing to another without extensive training. So it's a very specialized process. So processes go on. Between the processes, the wafers are monitored for process execution and so on, how well those processes have worked, are there any shortcomings and so on. Then wafers are transported around the fab, as you just saw in these little FOUPs, and overall manufacturing is monitored by module and integration engineers that constantly monitor what is happening on every, throughout the fab. So normally what happens is that the FOUP will come with 25 wafers in it. It will have a barcode on it. Actually, each wafer, when it starts, it's printed with a little barcode that you can barely see just at the very rim, the outer periphery of the wafer, so that each wafer could be tracked. So it starts live, it will go through, and when it arrives at a tool, then there will be some operator standing there, and they will have a barcode reader, just like at Walmart or Kroger. So they will scan the FOUP. They will scan a thing that every worker has to identify who the worker was who performed the operation. Then there will also be a barcode on the tool. They will scan that. So there are 3 scans that are done: the material in the FOUP, the operator, and the tool. And all that information immediately goes into the central processing computers, and engineers who are monitoring can see where the different wafer lots are. So these are numbered lots that are going through. So there may be lots that are coming that have got devices from Apple on it, or AMD on it, or Qualcomm on it, or NVIDIA on it. They're all going through various different lots for different process generations and technologies. So all of them are together. It's not that they're processed wafers separately. The same fab is processing at the same time wafers from many different companies, but they are all identified through a different lot identification. They all go through whatever operations needed. And then statistical process control, or SPC, is widely used, that every process has got statistical limit, or a lower limit and an upper limit, that if the etch is there, it cannot be more than this deep or more than that shallow. If deposition is something you are depositing on it, putting it down, say, a layer of metal, it cannot be too thick, cannot be too thin. So all of these SPC information is there for every single process. If it strays from that process by certain, say, 1 sigma, 2 sigma, whatever, then bells start ringing and people get informed and they need to check what is going on. And Intel people, say, sitting in there in Santa Clara in California, they get a call, oh, my fab in Israel, they are having some problem in the fab there because that particular tool is not performing very well. Do you have the expertise to figure out what exactly is going on? So there can be a worldwide collaboration on this. That is quite usual. So if we can very quickly look at that, there's one little video here shortly.
It's a complex superhighway most of us have never seen and will never travel. It's more than 27 miles of multi-level thoroughfares on which 1,700 autonomous vehicles shuttle Intel's most precious cargo. This is the Automated Material Handling System, or AMHS, at Fab D1 in Oregon. Intel runs overhead transport systems like this in every single one of our 6 chip fabs worldwide. The boxes you see scooting along are FOUPs, or front-opening unified pods, which carry as many as 25 wafers on their weeks-long fabrication journey from blank silicon disks to wafers, each containing hundreds of Intel chips. Let's take a closer look at Oregon's wafer superhighway that connects 9 buildings, including D1X and D1D factories. These 2 factories together are about the size of 12 American football fields. 24 hours a day, 365 days a year. FOUPs start, stop, swivel, turn, lower, raise, load, and unload. Every hour, the 1,700 move at least 16,000 times. They take wafers to the manufacturing tools that create the interconnects, the metal layers, and the often billions of transistors that comprise a single Intel microprocessor. The 200-pound pods travel at about 7 miles per hour. This is the master grade, an air traffic control center minus any humans. It makes sure each foot stops at the right tool at the right time. It sits in a data center just outside the factory. AMHS engineers load it with algorithms that transmit directions to over 100 smaller control centers scattered across the RA factory complex. This tool, called a train, is 48 feet long and is equipped with two 28-foot-high robots. The robots move back and forth on a track and use their robotic arms to grab FOUPs scheduled for departure to the next tool. The train is large enough to seat about 1,000 FOUPs. Many of these tools, including the train, were designed by AMHS engineers to store and transport FOUPs more efficiently. What engineers design, deploy, and learn here in Oregon, because it's a development fab, as well as a high-volume manufacturing facility, they transfer and share with other AMHS teammates in our factories around the US, Ireland, and Israel. The worldwide AMHS team lives by the motto, the heartbeat and blood flow of the fab.
Okay, so you just saw that. So they mentioned Oregon. Oregon's very important for Intel because in Oregon they have got what they call the R&D fabs, where they actually develop the processes for making the chips. But it's also a high volume manufacturing fab where actually chips are also produced there. In Arizona, they've got 4 or more and more fabs are coming up there. They're all high volume manufacturing fabs. They've also got their packaging and testing development facilities in Arizona. They've also got fabs in New Mexico. They are now building here in several fabs in Ohio. Then internationally also they've got fabs in Ireland and they've got fabs in Israel. Those are their 2 big international manufacturing locations. And they're currently also building in Germany, a set of fabs in Germany. So they're, but Oregon is very important to them because that's where they develop the manufacturing processes for new generations of chips and so on. So they employ the bulk of the PhD type people there in Oregon to develop the fabrication processes. And once developed, then those processes are transferred by engineers to actual volume manufacturing facilities in order to carry out wafer manufacturing. So there can be different types of manufacturing, like there is, depends on what type of devices are being made. So these days, most of what is called chips are what we call it a CMOS logic chip. These are the processors that are used in our phones, tablets, computers, and so on. And there's also memory chips that are manufactured, but memory manufacturers are specialized. So Intel doesn't make too many memory chips. They're mainly a processor manufacturer. There are companies like Micron here in Boise, Idaho. They make memories. They specialize in memory chips. And they also, Samsung is now the world's #1 memory chip manufacturer. Also SK Hynix in South Korea is a memory chip manufacturer. Other types of silicon chips are made like microelectromechanical systems, CCDs, CMOS sensors for cameras and so on. But the bulk of what we manufacture and what semiconductor industry is the CMOS logic chips. Then within that thing, there are various so-called process generations that refer to how small everything is. So right now we are at 3 nanometer technology node, and it's a lot of it's just basically discussing how small these things are, and there's not much relevance to that. It's used as more or less as PR terms as to how good somebody's technology is. So the next thing is that when a device starts, they make first devices out of it. When it comes out, it's called first silicon. And it usually have quite a low yield because it is a not developed process. So on a wafer, you may only get, say, 20 or 30% good devices that work, and the rest are dead, they don't work. So the next thing that is to be done is to improve all the processing, find out where the failures are, what is causing the problems, and fix all that processing so that the yield gradually goes up. That's called the yield ramp. So the yield typically starts with a new device, let's say 20-25%, it goes up. If it can reach, say, 85 or 90%, then it's a good yield. And at that point, everything is fine, and all mature processes will give you about 85 to 90% yield. Most companies are very secretive. They don't tell you what the yields are and so on. They keep it secret between themselves and their clients. But 85 to 90% are what they all aim for. There will always be some failures, no matter how well you have perfected your technology. And devices are sold as process wafers in so many. So if Apple is going to, say, buy chips from TSMC or Samsung, then they will simply buy these wafers, and then they have a separate contract for the wafers to be sent somewhere else to be packaged. Okay, here is what a wafers. Now we start to look at it in a little bit more detail. What a wafer actually looks like, fabricated wafer. So it all starts with silicon, right? So you saw that there's a silicon disk that is the wafer, and everything it comes on that disk in layers. So it's somewhat like making a pizza or a piece of cake. So there are various layers. So here it's listed from top to bottom, and it's color coded like that. So you start with the silicon wafer, and you do something called isolation structure formation. What it is that is when you have got so many transistors on the same die, there are billions of them, then they can interact with each other. They can talk to each other because they are sitting very close to each other. And that is undesirable. You don't want that to happen. Each transistor should be an individual device. So in order to make them not talk to each other, you have to isolate them separately, isolate them somehow. So one thing you can do is maybe etch a moat all around in a piece of silicon, so that there's like a moat all around, and there's a raised part in the center where you can make one transistor. And then every transistor sits in its own little island, separated by little etched moats. Then if you do that, then that's a type of isolation. So then, because of the presence of that etched silicon, deeply etched silicon, transistors will not be able to interact with each other unless you want them to, through electrical wiring. So that structure is called isolation structure. That's the first thing that they do, is form those structures on silicon. Next, you will form what is called a gate oxide growth, which you simply put that in a furnace. We'll show it to you. At about 900 degrees Celsius, it is red hot. Pure oxygen gets passed over it, and a very thin film of silicon dioxide gets formed everywhere on the wafer. That will form what is called the gate of the transistor. Yeah, we'll talk about that more later. Then the transistor, apart from a gate, the transistor has two other regions called source and drain. Those are formed next. And once you have done all that, the blue portion, you are here, then all the transistors have been formed inside the isolation structures. Next, what you do is you interconnect these transistors as needed in this ochre type color that you see. There's a layer which is called polysilicon metallization. So you basically make wires out of silicon itself and connect the various transistors according to the design that the circuit design is produced, right? It all started from the design. And once that has been done, then you think that, okay, I've completed a chip because the transistors have been made and they've been interconnected, fine. But remember, these transistors have got hundreds of billions of transistors on it. So the interconnection is extremely complex. So the further wiring connections need to be made between different parts, like between registers and arithmetic logic units, various parts of memories, and so on. That cannot be done at this level of polysilicon metallization. You need more interconnection wiring. To do that more interconnection wiring, you first put down this red layer of extra silicon dioxide to insulate everything. And then you etch little tiny holes in it and fill them with a metal like tungsten. It's called a tungsten plug. And that has got holes that connect to this ochre layer in specific locations. And then you put down in this green thing, you put down some wiring pattern. And that wiring pattern used to be copper, used to be aluminum, but these days it is copper. And there's further work going on to replace it with another metal, an exotic metal called rhenium. So rhenium or ruthenium, I confuse between the two. So that one is going to replace some of that metallization. And then there are several layers of this that alternate the insulator, which is in red, and then the conducting wiring in green, another insulator conducting wiring. There can actually be 20 or I've shown a few, but there can be 20 or 25 of those things. To connect all those hundreds of billions of transistors, you do need that many layers of wiring metallization. So you can see why this is so complex, because there are isolation structures, there are transistors, there's local interconnections here in polysilicon, there's several layers of alternating layers of wiring and metallization. Every time you go to this red thing that is a layer of silicon dioxide, you have to etch specific holes called vias in different locations and then fill it up with tungsten to make a connection through, because the red thing itself is electrically non-conducting, and then make a wiring pattern on top of it. So that's where all that complexity lies in doing all those processes. Every time they do that, any process, they check it using specific tools. They usually come from a company, it's well known in the industry, it's called KLA-Tencor. They make equipment that you'll see scattered all around the fab. They scan wafers. So you do a process, you get something scanned, you send the wafer for scanning. It's like they're doing an X-ray scan. It doesn't, yeah, it sometimes does use X-rays. And it comes out with a wafer map that shows where possible problems are, maybe where the dust particles are, where the broken connections are, and so on, so that people know if problems are arising, where those things are. So that is the structure. Now in the wafer fabrication process, Dr. Kyle will go into more detail about specific processes, but you do various processes. So processes are like silicon dioxide growth that I just mentioned, done in a furnace at high temperature. Silicon dioxide deposition, which is done in a different tool, and then so growth of silicon dioxide is different from deposition, because growth you can only do on silicon, right? Because if you are growing silicon dioxide on silicon, then you use up some of that silicon, because you go from Si to SiO2. So you use some of the silicon to make silicon dioxide, right? That's called growth. But once you are doing wiring, then you are working on, say, on a metal layer where there is no longer silicon below you. So you cannot grow silicon dioxide anymore. So you actually then deposit silicon dioxide. You send two gases, one called silane, SiH4. It's like methane is CH4. Silane is the analog of methane. It is SiH4. You send it through a tube. You send oxygen through another tube, and the wafer is hot. They react on that hot wafer, and reaction takes place, and silicon dioxide gets deposited, and the oxygen gets removed as water vapor. So that's a deposition process. Then you can deposit various metals, what is called material blanket deposition. That is for making wiring connection, you need metal. So what you do is you deposit a metal everywhere. That's why it's called blanket deposition, which means deposit everywhere, indiscriminately. It goes all around. It's a complete coverage on the wafer. Once you've done that, then you do a lithography step to define how the wiring pattern would actually look like. And then you remove metal where you don't want it, so that you leave just the wires interconnecting them. So you do the lithography to define, so you deposit the metal, which goes everywhere. Then you do a photolithography step to define what the wiring pattern would actually look like. And then you will do a dry etching or plasma etching. We'll show you all the tools today to remove the metal from where you don't want it. And then it is all done. You can also do a process called ion implantation, which is important. And before you do lithography, you sometimes do a CMP called chemical mechanical planarization. And that is because lithography requires very flat surfaces. But as you start to build up your chip and you add on all these layers, the wafers become kind of wavy. There develops a topography on it, right? So that makes doing photolithography harder, because it requires very flat wafers, very flat surfaces. It's like you are taking a picture with a camera, right? You have to, everything has to be, subject has to be in good focus. If you are a little bit, closer or farther away from the lens, your picture will not be very sharp. It's exactly the same thing, as because you are ups and downs, not everything will be in sharp focus when you want to do photolithography. So you need to planarize it, and that is done using a process called CMP. And one other process that is used is wet etching, also called stripping. and you can do wafer cleaning, wafer inspection, inline testing. These things are all done. So lots of processes that need to be done that we'll be telling you more about. So very quickly, let's go through some of these processes. So for silicon dioxide growth, I already told you how you do that. You put a wafer in a machine called that's just a furnace, running at high temperature, about 900 degrees Celsius, with oxygen in it, and it just grows a layer. You don't need to do anything. It grows a layer, very thin skin of silicon dioxide. The skin is very thin. It's like, think of an apple and the skin of an apple. It's very, very thin. Another way you can do that is you can grow the oxide in steam rather than in pure oxygen. If you do that, then you can grow thicker oxide more quickly, but it hasn't got the same good quality as just an oxygen oxidized silicon is. So it depends on what type of oxide you need. You can do either pure oxygen oxidation or oxidation in steam. So the oxide thickness could actually range from 1 nanometer or less to up to 100 nanometers in thickness. So it is thin oxide that gets formed. The wafers come out looking colored, and you can actually see the play of color on the wafer, right? Blue to green. Because as you change the orientation and the angle you are looking at, the color looks different. It's not a real color, there's nothing colored there. But it is just the fact that very thin layer, transparent layers look colored. So it looks like that. Okay. Here's so that was about silicon dioxide growth. This is silicon dioxide deposition. Sometimes you want to deposit silicon dioxide rather than grow it. So in that case, I mentioned you this process. You take this gas, silane, SiH4, react it with oxygen. It gives you silicon dioxide and this steam or water vapor, right? This is a balanced chemical reaction, isn't it? A balanced reaction. It is. And silane is dangerous. It is pyrophoric. That means if this gas comes out in the atmosphere, it will spontaneously burn. With no matches, no nothing, no thing, it can very easily start burning. So it's dangerous. And that is an important safety point, that a fab is a dangerous environment. It is like a big chemical plant with lots and lots of dangerous chemicals in there. There are poisonous chemicals, there are corrosive things, there's dangerous acids, there are very bad alkalis, there are dangerous or toxic gases, things that can burn on their own and so on. So it has to be all carefully monitored with sensors and regulated and so on. But things have been perfected to such a high degree of perfection that normally everything works fine. So in this process, everything sits inside a chamber. So this is your wafer, this thing is blue, and gases come from up above, and then so there's a low pressure gas inside the chamber, and then you send microwave. So this RF is a microwave source, just like the microwave in our ovens, but much more high-powered microwave. It comes and goes inside, and where the electrical discharge is produced in the gas, and we form what's called a plasma. That's what calls the aurora displays, or the color and neon tubes and neon signs that you see is a plasma. So the gas begins to glow, and Dr. Kaya will show you some glowing gas plasmas later in the afternoon, right? So we'll all get to see that. So that plasma, then in that plasma, this reaction takes place, and silicon dioxide gets deposited on the wafer.
All the fluorescent tubes are plasma discharges.
Yeah. Sure. Yeah. Absolutely.
White
So
lines.
plasma is all around us in a sense, right? And then I'll leave other things for Dr. Kaya to describe, but plasmas are also used in a process called sputtering or sputter deposition to deposit metal. So what you do is you place, that uses a completely different tool, but you place your silicon here, your wafer, and this target, so-called target, is a plate of the metal that you want deposited. You create a plasma there, then the charged ions in the plasma go and hit the target with a lot of force, and they dislodge some particles, some material from that plate. And that comes out, and guess where it will go? It simply deposits on the metal, right? So the entire thing gets covered with a metal. That's called sputter deposition process. So that is also widely used. Then you can also use plasmas again. So plasmas are everywhere in the fab. You can use other plasmas to remove material. So not only you need to add material through sputtering, you also need to remove material from where you don't want it. That is called etching. So that etching is also to create structures like these etched structures. So that's also done by plasma, and I would leave it for Dr. Kaya to tell you more about how this exactly works, but there are tools that carry out plasma etching. So plasmas are used for both material deposition and material etching. So, so you see the way it works, what is important to understand, to take from it, is the way the entire processing of wafer works is by the repeated application of the same process many, many times, right? You deposit material everywhere, right? That's called blanket deposition. Then you define a structure on it using a process I will tell you called lithography, which defines a structure on it. And then you put that in an etch machine to remove material from where it's not needed, and leaving you with shaped material. It could be shaped silicon dioxide, it could be a shaped metal like copper or something, and that process then gets repeated over and over again for many, many weeks to gradually build layer by layer that structure, where transistors sit at the very bottom, as we have seen, and the wirings go on top. On various layers will carry the different layers of wiring. One important process that is done is, and I've not touched into this, but this is extremely important, it's called ion implantation. And that is done to generate what is called N and P-type material in semiconductor, which you'll also get to learn later, but that is done using a separate tool called an ion implantation tool, right? So we'll also cover that. Okay, very, very important is this photolithography. So I'll take a few minutes to describe this, because this is the queen of the processes. This is the most important process that happens in the fab. This is the thing that companies compete about, that how well they can do this, and that is defining the actual structure. So depositing a material all over the wafer is not a problem. Etching is a little bit tricky, but that can also be done. But defining the structure in which to etch something is what photolithography is all about. So what here we are doing is so what you do is you take a wafer, right, and you cover the wafer with, so you have deposited a metal, say, on a wafer. Now the next thing that you do is that you take a plastic which is dissolved in a solvent, so it is like nail lacquer type thing. And you put that on the wafer and you spin the wafer at high speeds. Then that plastic solution gets spread all over your wafer uniformly as a thin film. Then the wafer stops and you have got a thin film of plastic covering everything. It's been like wrapped in plastic that's covering the entire wafer. Next, what you do is you will take a glass or quartz plate with the required pattern that you want on it. It's been printed on it. That plate is called a mask, a photo mask, right? And that will put that in a machine like this and will shine ultraviolet UV light from the top. So that light goes through the mask plate and it gets blocked, because some of parts of that plate, we'll show you the plates in the labs, are covered with chrome, with metallic chromium. So that will block the light. Some other parts are clear, so the UV light will go through that. So the light itself then becomes patterned because it just passed through that pattern mask plate. And that light pattern falls on that plastic covered wafer. That plastic is no ordinary plastic. It is what is called a photoresist. It is sensitive to light, very much like photographic film, just like that. So when that light falls on it, wherever the light falls, it causes some changes in that plastic. So after this step called exposure, you take out that exposed wafer and you put it in a wet material called a developer, and that will eat away all the plastic wherever the light hit it, but it will leave it wherever the light didn't hit it. So that's how you create what's called a stencil. It's like a plastic stencil has been created. So there's a layer of plastic, but now there are openings in that plastic, in that photoresist plastic, there are openings. And through the opening, you can see the wafer down below. It has been exposed. But the rest is still protected by that plastic. Then you can send it for, say, for etching. Then the etching will not happen wherever it is protected by the plastic, but wherever there are openings and the underlying material is exposed, etching will take place there. So you do that, and after that process, you can just remove the plastic by dissolving it in, say, acetone or something like that. And then you are left with that pattern material. So that is the way that it will work. The photolithography has got its own interesting history, because that is the history of semiconductors itself, how things have progressed. So in the very early days of ICs, we used to use mercury lamps as UV sources to do photolithography. And that had a wavelength of 365 nanometers, and it was sufficient for whatever we wanted to do there. But then we wanted smaller and smaller features. But the problem is that if you have got masks with very small structures on them, as light goes through it, it spills out into regions which should normally be in a shadow, right? So if you have got a slit, imagine a slit. If you send light through a slit, you would imagine that it will keep on going like this shape of the slit. But it doesn't. It can go into where it shouldn't go. It goes sideways as well, a phenomenon that in optics they call diffraction. So that's why sometimes you see the images of stars and it shows these little streaks coming out, you know, in the pictures. That is due to diffraction, because stars are supposed to be a point of light. How come these are these streaks? That is light going into where it should not be. That is diffraction. That happens a lot in these small structures on photomasks. That is the big problem, right? That people have to overcome somehow. It turns out that if you use light with shorter wavelengths, then you can control that diffraction. So everything has gone to shorter and shorter wavelengths. So from 365 nanometer of UV mercury lamp, people moved to 248 nanometer light, or UV light, that is generated by these krypton fluoride laser sources. And then even that proved insufficient. So during the turn of the century, they developed these 193 nanometer argon fluoride lasers to generate even shorter wavelength light. And later on, they developed something called argon fluoride immersion lithography, which works in an interesting way in that the wafer sits and then is covered with a layer of very pure water. And the lens actually sits inside that water. So there's a water between the lens and the wafer. And due to optical reasons, that leads to higher resolution lithography. That's called ARF immersion. And these days, we are in the era of what is called extreme ultraviolet lithography, or EUV, which works at an incredibly short 13.5 nanometer. We're actually pushing into the soft X-ray region now. So this is slowly UV will be turning into X-rays. Actually, if you go lower than 10 nanometers or so, then you are basically talking about X-rays. So it's gone there, that thing. There's a new iteration of that called high NA, or high numerical aperture EUV lithography. It's now being used. And the industry does what's called mix and match. That is, when you are making a chip, sometimes you will use 193 nanometer ARF, sometimes ARF immersion, and sometimes for very critical layers, with the smallest dimension, you will be doing this EUV lithography. So it is not that industry no longer uses that. All the tools will be present on the fab floor, and they'll mix and match it. So larger structures, they'll send it to 248 or 193 nanometer machines. Smaller structures will get the very critical ones at the gate layer and so on, or the micro vias will be done using EUV these days. So that's, so I wish I had more time to describe that, but time runs short. So there is a view of this EUV lithography, because that's the latest in the fabs.
In the 21 years I've been reporting at Intel, I've seen amazing products and the machines that help create them. But the machine I'm about to show you blows my mind.
That's the EUV lithography. That's the latest.
And I'll show you. This is it, an EUV, or extreme ultraviolet lithography system.
It is likely the most complicated machine humans have ever built. It pushes Moore's law forward, and chip makers cannot produce leading-edge chips without it. But more on that in a moment. The EUV machine is a reality after 35 years of sustained research and development from lithography leader ASML, Intel, TSMC, Samsung, and others. Delivering just one of these tools to Fab V1X in Oregon took 3 747 cargo planes, 40 freight containers, and 20 trucks. The school bus-sized machine comprises 100,000 parts and weighs nearly 200 tons.
So what exactly does this EUV machine do?
Intel co-founder Gordon Moore observed that the number of transistors crammed onto a processor doubles roughly every 2 years, a cadence that has continued for more than 50 years and has long been known as Moore's law. The more transistors and components on chips, the cheaper and more powerful they become. Chip manufacturers use lithography machines to inject circuit patterns onto silicon wafers. For decades, they have kept shortening the wavelengths of light on lithography machines to print features for ever smaller transistors. In pursuit of Moore's law, Intel engineers have produced inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. Intel and other chip makers have also adopted processes such as double and quad patterning and water immersion lithography to get the most out of today's 193 nanometer wavelength light. But to make transistors even tinier, the industry needs lithography machines that use radically shorter wavelengths. This EUV machine produces light at 13.5 nanometers. Compared to today's machines, that wavelength is more than 10 times smaller.
So how does this machine work? Put on your best thinking caps, and I will try to explain it simply.
First, extreme ultraviolet light does not exist naturally on Earth, so we have to generate it. Because this tool is so large, it needs 3 floors in the fab. Its laser, about 15 times more powerful than ones used to cut steel, sits on the level below the clean room. A beam transport transmits the laser pulse up a floor into the EUV machine, where a generator fires tiny droplets of metal tin, each droplet only about 1/3 the diameter of a human hair. And that powerful laser, flashing at 50,000 times a second, hits the molten tin. The metal vaporizes into a plasma. This plasma releases light in the extreme ultraviolet range. A collector mirror gathers the 13.5 nanometer EUV light and shoots it to a scanner, where it pinballs off extremely precise mirrors that shape the light into slits that create patterns of transistors and interconnects onto a silicon wafer.
See, wasn't that simple? Just a couple more remarkable facts.
Newer factories at Intel have ceilings 16 feet high. They are raised to 25 feet where these EUV tools rest, because it takes an overhead crane system to assemble the heavy system components. How precise are the EUV machine's optics? Here's the math. It's analogous to an astronaut standing on the moon with a laser pointer, targeting the tip of my fingertip here on Earth. ASML is already working on an improved version of the EUV tool that will offer even finer resolution lithography. Intel is currently the first customer in line to receive one of these next generation machines to prepare for the Angstrom era of computing.
Isn't this mind-boggling? Hope you enjoyed coming behind this door to see this marvel of engineering and a tribute to human ingenuity. Thanks for watching. I'm Rob Kelton. In the 21 years...
Okay, now very, very quickly, maybe 2-3 minutes more. There's a process that I mentioned called planarization in the industry, where you can just take a wafer with some topography on it and simply scrub it using a pad with some scrubbing slurry liquid chemical to make sure that it's very clean before it can go into the lithography machines. That doesn't happen initially, but later on, as the wiring layers get built up, 5 layers, 6 layers, 7 layers, it gets increasingly uneven. Then you need to do that before you can do the next lithography to get wafers that are very plain. Then in wet etching stations or tools, you can use wet chemicals to perform etching, not for very small features, but for relatively large features, you can still do wet etching. And finally, there is what is called process integration, which is this is a field where you integrate all the different processes, the deposition, the etching, the lithography, the planarization, to make sure that they all work towards the goal of making a chip. So, and there are separate engineers that do that called process integration engineers. So there are lithography engineers, diffusion engineers, unimplanted engineers, sputter engineers, and CMP engineers, but there are also process integration engineers who make sure that all of these work together to build that chip. So that is basically an overview of how we fabricate wafers in the fab. It starts its life, and as I said, it gets printed with information around its rim, and then it will take anywhere from 4 to 8 weeks to make its way out of the fab after it's completed all the processes. Then it can go for testing and packaging. And that testing and packaging, I and another colleague of mine will be describing to you after lunch, so we'll look at that. But now we need to look at how these different processes, they're only described in brief, in a little bit more detail, how these things work and why those things are important. So here's my colleague, Dr. Kaya. Please. Thank you.